Let's do this in your, oh, good morning, ladies and gentlemen. I got too excited. Do this in your notes now. Bubba did 500 joules of work carrying a backpack to the top of the bleachers. My first question, what was the UGG of the backpack at the top? 2, if you dropped it off the top, how much kinetic would it have just before it hits the ground?
Pause this. Do it.
Do you have to do any math here?
This is a knowledge question.
Yeah, so let's see. So if he did 500 joules of work equals the change in energy, and that equals the UGG, which equals the kinetic energy. So the work is going to equal the UGG.
Yeah.
So it's going to be 500.
Yeah. So the question is, why does it equal the kinetic energy? I think you're going to have to do that pyramid.
Oh, the pyramid?
Yeah.
Okay. So we know that the conservation of energy, the energy total in the beginning equals energy total in the end. The energy total is going to be...
We're talking about mechanical energy, so it's K plus UGG, kinetic plus gravitational potential energy.
Equals the total energy at the end, kinetic plus the UGG at the end. And at the very bottom, it's been dropped off the top, right?
Yeah.
Also at the top, it has all UGG, right? And at the bottom, it's all kinetic.
Well, and you did the work to get to the top.
Oh, and the work is, what was it, 500?
500 joules. You did the work to get to the top. That's stored as gravitational potential energy. And on the way down, the potential energy decreases, the kinetic energy increases. So, boom to boom to boom.
There it is, there it is. And if it seems easy, it's because it is.
It is.
Right? You just have to think about this and, always a good idea to write the pyramid. Always. Okay. Energy is the ability to do work.
This sounds like something we've talked about before. Work equals energy.
Work is the transfer of energy by mechanical means. So if you're walking up a bleacher, if you're picking up a pumpkin, whatever it is. Work is how much force is exerted on an object times the displacement it moves in the direction of the force. I was like, what does that word say?
Yeah, this is all review.
Force times displacement, or force cosine theta displacement. Okay. We just did this.
Here's the pyramid. This is the law of conservation of energy, specifically applied to mechanical energy.
Yeah.
Because there's so many different kinds of energy.
You should always start with this. This is, you know, you need to, even I do this still. I mean, it helps me to write it out. Okay, let's do our thing.
Pumpkin.
So I've got a pumpkin in the back, and it has a mass of 3.75 kilograms.
Let's go play with the
take a look.
pumpkin.
Okay, so here is that pumpkin. 3.75 kilograms of a pumpkin right here. Okay,
Yeah.
and ooh, it's cold. And I'm going to start with it on the floor. And what I'm gonna do is I'm going to pick up the pumpkin, do work and pick up the pumpkin, and I'm going to throw it in the air.
Okay.
And what you guys are in charge of, aka Mr. Boykin, is I want to know at what point does the pumpkin leave my hand, and you can use these markers to help you out.
That's 1 meter, 2 meters, 3 meters. That's 4 meters up at the top.
And the other thing we want to be looking at is how high does it go?
Yeah. So and I'll be doing that as well. I'll be over here on the other side of the classroom. I'll keep track of where I think your hands were when you let go, and I'll keep track of how high it went.
All right, you ready for this?
All right, let me get in position. All right.
And time to do some work.
Okay, I'm gonna say your hands were about 2.1 meters, about there.
2.1?
2.1 meters, and up at the top it was about 3.9 meters.
Okay, let's write that down. 2.1 and 3.9.
Yeah.
2.1, 3.9.
In fact, we could make a diagram.
Let's do a diagram. Always a good idea. 2.1, 3.9. Okay, so floor right here.
Uh-huh.
Bloop, 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 bloop. And I let go of the pumpkin right here.
Yeah, 2.1 meters.
Okay, that was 2.1 meters from here to here.
And
then what was it?
3.9.
3.9. We'll just call it right there. Okay, right there. And the air. Okay.
All right, well, Let's see.
Where should we call UG? We
We
should
sh-
make it 0.
I think where it left your hands, because you're
Okay.
doing work giving it gravitational potential energy. So UG is equal to 0. Actually, you're not giving it potential energy, you're giving it kinetic energy.
Yeah. And then it's the highest up here, right? So that's where the UG is going to be max at. And what was that equation for UG?
MGH.
MGH, okay. And then let's talk about kinetic energy.
So the kinetic energy is 0 at the top, isn't it?
Uh-huh. So kinetic energy equals 0, and it's going to be max right here.
Yeah.
Equals
Okay,
max.
so MGH, that was 3.75 kilograms is the mass.
And I did work up in here.
Up in here. Up in here.
Okay, so what sort of things can we find?
Well, let's find the gravitational potential energy
Let's
up
do
there
this
at the top.
first. Yeah. So let's go. 9.8 is my. Oh, sorry, not mass. Start with my mass first.
It's 3.75. You're going to run out of room.
I know,
Why
I'm
don't you do
gonna
it
write
underneath? Yeah.
3.75 kilograms times. And now, why is it a positive 9.8 again? Because we're doing work against gravity, right?
Yeah.
Meters per second squared. And then the height, well, it's going to be 2.1 plus 3.9.
And 3.9 minus 2.1.
Oh, sorry, you're right.
It's the difference in the heights.
You're right. This minus this, that's going to be 1.8.
1.8.
1.8? Okay, 1.8 meters. Yeah, so I just want to know this height right
Yeah,
here.
that's delta H.
Yeah, and the whole thing is delta, the change in the height, right?
Yeah.
Okay, so let's do this. So the UG is going to equal, let me get out my handwritten calculator, 3.75 times 9.8 times 1.8, and I get 66.2. We'll call it 66.
We'll call it 66 joules
66
of gravitational
joules of
potential
work.
energy.
Okay.
So if it's got 67 joules of gravitational potential energy, 66 at the top, and the kinetic energy is 0, what about when it left your hands, where the UG is 0?
Well, energy is conserved, and we just showed that the UG is going to equal the kinetic energy, right?
That's right.
So this is also going to be 66 joules.
Oh.
Okay.
So if we know the kinetic energy and we know the mass, what can we find?
Kinetic energy and the mass. Can't we find the work?
Mm,
No,
we
that's
can
for
find
force.
the work.
We can.
We know what the work is. The work is going to be 66 joules because that's where the kinetic energy
we
came
can find
from.
the velocity.
There you go.
That's what it is. Okay. So basically, we want to know, how fast. Well, I can use this again.
How fast is it going when it left your hands?
What was that equation for kinetic energy?
1/2 mv squared.
Right.
Multiply both sides times 2.
This
Divide
with
by the
this.
mass. Take the square root.
Boom, boom. Divide by the mass. Divide by the mass.
Take the square root.
Oh, square root. Square root. Okay, so square root of 2 times 66 joules divided by mass, 3.75, right?
3.75.
Okay, that's going to equal the velocity. And that is the square root 2 times 66 divided by 3.75. And I get, we're going to let 6.
6 meters per second. So it's going 6 meters per second. Wait a minute. We found out how fast it was going when it left your hands when you tossed that bad boy. And we use the law of conservation of energy to figure that out. That's remarkable.
Remarkable. Okay.
So now we know the work. What is work?
Well, how do we know the work? Well, the work is the change in energy, right? What did we just say the change in energy was?
It went from 0 on the ground up to 66 joules.
Okay, so the work equals 66 joules.
So you did work
From here.
from here to there, and it had 66 joules of kinetic energy. That work changed the energy to 66. On the way up, it went to 0, and the gravitational potential energy went to 66. So how could we find out, what could we find out if we know the work?
So we know the work, and we know the distance, right?
Yeah, it's 2.1 meters.
2.1 meters. Well, we could figure out the average force between here and here, right?
That's right.
Okay, well, work equals force times distance. And I have work in this. I could just divide by the D, huh?
And that'll give you the force, the average
Okay.
force.
So-
Remarkable!
So work divided by distance equals the force, which gets me 66.
Divided by 2, I'm going to say that's 33.
2.1.
Oh, 2.1. Oh, I'm sorry.
No.
Dog lips. Excuse me for swearing.
30, close though, 31, we'll call it 31. We're just doing all sorts of rounding today. Newtons.
So look at all the stuff we got, and all we did was see where it left our hands and how high it went. And using the law of conservation of energy and the work energy theorem, we found out how fast it was going. And we found out the average force. That's remarkable.
So yeah, do you want to walk through one more time or?
No.
Okay, they're good.
They can go back and watch it again.
In fact, my next task for you is Miss Moore tosses a pumpkin. I was trying to toss a bowling ball, but
It's not gonna, a little dangerous on the way down.
Miss Moore tosses a pumpkin into the air. Describe how we use the conservation of mechanical energy, the law of conservation of energy, to find out how fast it was going when it left his hand. Tell me, how did we use the law of conservation of energy to figure this out?
So stop this, and we just did it. Describe what we just did. All right. Oh, page 258.
Okay, 258. Let's do it. 258 has a really great little drawing in it. You guys should go here. Go to 258, and you know what? I'm even gonna ask you to draw this. I mean, this is good stuff.
Focus. Come on, focus. There you go.
There we go. So we have the ground halfway up and the top, and this is the baseball moving, and then we have kinetic energy and UG over here.
Yeah.
And at the very bottom, what do we know about the kinetic energy?
It's all kinetic and it's no potential.
Okay, and then what about the top?
It's all potential and no kinetic.
And then what about in the middle?
They're equally shared.
Ah, okay. And so the decrease in potential energy is equal to the increase in kinetic energy.
There you go.
The total energy is the combination of the kinetic and the potential. That's important. Okay. A 0.5 kilogram mass has a velocity of 10 meters per second. What is its kinetic energy? Start doing this.
That's K is equal 1/2 mv squared. That's 1/2 times a half times 10 squared. 10 times 10 is 100, isn't it? And half of 100 is 50, and half of that is 25. I bet it's going to be 25.
Times 0.5. Don't worry, guys. We'll plug it into the calculator.
Can't believe Mr. Boykin. You can't believe everything the old man says.
10 meters per second. Don't forget to square. I'm always forgetting to square. Okay, so let's see. 0.5 times 0.5 times 10. Drum roll. 25! Woohoo!
The human calculator up in here.
He does it again. 25 joules. Okay, so.
Well, they could probably do that themselves. So I was just channeling the students.
Isn't that right, guys?
Yeah.
Okay.
So erase that.
Oh, erase it. So that was 25 joules. Do
Simple.
a water balloon slingshot is stretched, kind of like a rubber band, 1.5 meters with an average force of 16.7 newtons.
Now, I'm going to stop you right here. About 2004, the leadership, the student body office, bought a water balloon slingshot. It was used surgical tubing, and you had two big burly guys each had one end of the slingshot, and then somebody would put a water balloon in the saddle in between, and they would be over by the library, and they would pull it back, and they would fire the water balloon all the way across the quad.
What?
It would land over by the rock. It was hilarious.
Oh my gosh, in 2004?
It was right around then, and I tell you, you know how sometimes, you know, the leadership is trying to get people to
be
participate.
involved. Yeah.
I'm telling you, with that water balloon, people were paying attention.
How did they get that cleared?
Well, it was also when it was like 95 degrees outside,
Yeah.
so it was a cool thing
People
to
were
do.
loving it. Fun fact, Miss Moore was in 4th grade in 2000. Okay, and I had just moved to California.
Okay.
Oh,
so
actually, I was moving.
I don't know why they got rid of that water balloon slingshot.
why
I
would
think
they
there
do
might have
that?
been parental complaints.
Yeah, that's the first thing on my mind.
Okay, sorry about the digression.
Okay, so a water balloon slingshot. They're like, I'm gonna stop you. A water balloon slingshot is stretched 1.5 meters with an average force of 16.7 newtons. How much work was done? How
What's
much
work?
energy? Okay, so what do we got here? We've got the displacement, 1.5 meters, and it's stretched with an average force of 16.7 newtons. I mean, technically it's at average. But it still works the same. How
Yeah,
much
yeah.
work?
Work is force times displacement in the direction of the force.
16.7 newtons times 1.5 meters.
24, 25 something, isn't it?
16.7 times 1.5. 25!
Woohoo!
Dang, all these.
So
even
25 joules of work was done.
numbers. Okay. How much energy is stored in the slingshot?
Well, what does work do?
Well, work changes energy. Work equals the change in energy,
Uh-huh.
and that equals the UG, the energy stored in spring. So as
Actually,
I
it wouldn't
do
be
work-
UG, that would be USP.
Oh,
That's
thank
gravitational potential energy.
Thank you.
That's
Well,
potential energy stored in the spring.
So UG would be the energy stored as I pick something up relative to the ground, is
Yeah.
gravity. But what Boykin's saying is a really good point.
It's stored in the slingshot.
It acts like a spring, right? When you pull this back, okay, so it's the exact same thing, but we just put an SP for spring.
There you go.
So that means that if the work is this, that means that the energy stored in our spring, in our slingshot, is also going to be
25 joules.
25 joules.
Sweet!
Okay. How much work can the slingshot do on a water balloon when it is fired?
Well, duh.
Well, the same amount.
Remember that equation works in both directions.
Yeah, so we can go this way, but we can also go this way. So the work done is still going to be 25 joules. Nothing's changing here, right?
No.
How much kinetic energy would a water balloon have the instant the slingshot finished doing work on it? So we let it go, right?
Yeah.
Okay. Well, we can continue this, right? This is also equal to the kinetic energy,
Yep.
and that's what we're talking about here, right?
Well, now,
Kinetic energy?
the potential energy stored in the spring does work.
Mm-hmm.
That work is 25 joules, and that work that the slingshot does becomes kinetic energy.
It becomes kinetic energy, so it turns into kinetic energy, and nothing's going to be gained or lost here. Energy's conserved. So
That's right.
25 joules.
In the ideal world.
In our perfect world. Okay. How fast would a 0.5 kilogram water balloon be going the instant it left the slingshot?
We know the kinetic energy, we know the mass. Boys and girls, pause this, do this yourself. Okay. We have done this a bunch of times. That's going to be 2K divided by m square root.
Mm-hmm.
So it's
So here we go. 2 times the kinetic energy, which is
25.
25 joules.
Divided by half a kilogram.
0.5 kilograms. If it's 25 again. 2 times 25 divided by 0.5, 10.
10!
The velocity is 10.
It's going 10 meters per second when it leaves the slingshot.
Okay.
See how this stuff works? It's actually a pretty straightforward process.
Kind of fun.
Yeah.
Oop, did I just go into it? No, we're good. Oh wait, did I? Kinetic energy, that's the one we just did, right? No, this is the one we just did. Okay. If the balloon was fired straight up, what would happen to its velocity as it rises?
Well, it's like why I can't dunk the basketball. I'm going really fast when I first get off the ground, but I slow down as I approach as I dream of approaching the rim.
Dunk it! The balloon slows down, right?
Slows
the
down.
velocity decreases, the velocity slows down because it's got to get to 0 at the top,
Yeah.
wherever that is. If the balloon was fired straight up, what would happen to its kinetic energy as it rises?
Well, if it's slowing down,
Okay, well then if it's slowing down, the kinetic energy is also going to be slowing down, right?
yeah,
Decreasing.
because the kinetic energy depends on the velocity, and as that velocity decreases, so do the kinetic energy.
If it is fired straight up, what would happen to the balloon's UG as it rises?
Well,
Potential energy. Well, you have more potential to hurt yourself way up there, right?
yeah, it goes up, it increases.
It increases, it goes up. And then, how much UG would the balloon have at the top of its flight?
Well, conservation of energy would say that kinetic energy is changed into potential energy.
So it'd be the same.
Yeah, I think there's something in the book that kind of illustrates that.
253. Oh, look at that. Okay, so again, we have another graph here, beginning, middle, and end. And at the beginning, we can see when the ball is first thrown into the air, it's all kinetic, no UG.
Yep.
And then, oh, and I love how it does this. It says that UG is, that's the ground, that's where 0 is.
0 is, yeah.
Okay, now as the ball goes to the very top, goes to the middle, I mean, during the middle of the time period, when the ball's at the top,
Yeah.
now we have our UG is, well, it's everything from kinetic's been transferred into UG.
Yeah, because it has to come to a stop at the top.
And it's not moving at all, so 0 kinetic.
Yep.
And then once it comes back down, that's the end. It's all been transferred back into kinetic and no UG. It's kind of like a seesaw.
It is. I like that.
Okay.
So how much potential energy will it have?
The same.
25 joules.
Yeah, the same. 25 joules. Okay, so how high above the release point would the 0.5 kilogram balloon fly? How high again? So we said, was this when so we still have the.
Well, we've got 25 joules
right?
of potential energy at the top. What's that equation for gravitational potential energy?
Equals mgh. And we want to know how high, right? We want to know this, right? Well, we know this is 25. 25 joules equals, I could just divide by mng, right?
mg, right.
My
So that's going to be
mass
0.5 kilograms.
Times my gravity. And that's going to give me my my height.
Yeah.
Okay. Dang, this is kind of like a long problem. You can do so much stuff. 25.
It's just a bunch of small problems.
0.5 times 9.8. Okay, I get
Just
5.1.
parentheses on the bottom.
I did.
Good girl.
Yeah.
So how much you got?
I 5.1.
5.1 meters.
I use parentheses on the bottom because
5.1 meters. That'd be up above the ladder. Oof.
that's pretty high up there.
That
That's
is.
really high up there.
That's right.
I use parentheses on the bottom because if I don't, it'll do this divided by this times this, and I
Yep.
want this to be together.
Yep.
For my people who are.
Wait.
Oh, sorry. So how high above? Oh, the Sun Star. The Sun Star. There we
Who's
go.
ever heard of the Merced Sun Star?
Have you guys ever heard of a newspaper? This is a newspaper,
A newspaper.
and it's my parents just discontinued the Merced Sun Star, but we still get the San Francisco Chronicle. It is a paper that has news on it.
Oh yeah, I see
God
that.
forbid you don't get your information from Twitter. Okay, and this newspaper is from Tuesday, December 10th, my mom's birthday, 2002. And I wanted to read this article
Wait a
to
minute,
you guys.
December 10th. Oh, that was 18 years ago.
Oh my gosh, it feels like it was a lot more recently than
How many of you
that.
guys were born in 2002?
Well, I don't think were you guys alive then? This is before you were alive.
No. No, maybe.
I think it might be.
Seniors could be 18.
Okay, so here is under the accident category. Brick tossing incident leads to major injury. Merced man airlifted to Modesto Hospital for treatment of major head injury. Here we go. A Merced man's experiment to see how far he could toss a brick into the air resulted in a split head and a trip to the hospital on Sunday. The victim, whose name or age were not available, was taken by air ambulance to a Modesto hospital for treatment of a cut to his head. Merced Police Detective Kurt Gorman said the injury occurred when the victim was hit on the head by the brick he'd thrown into the air to see how high up the object would go. Gorman said the incident came to light around 2:30 a.m.
2:30 in the morning.
Up to no good when he was called to the 600 block of East Main Street to respond to an apparent gunshot victim. On his way to the address, Gorman received a radio message canceling the call. They thought it was a gunshot victim. Officers at the scene learned the victim had not been shot, but that a brick had struck him on the head, knocking him unconscious,
Uh-oh.
Gorman said. It seems the victim, after drinking too much, God forbid,
Surprise.
began throwing the brick into the air. The problem was that after being tossed into the air, the brick would disappear into darkness.
Ah!
Undaunted, the victim continued the brick tossing experiment 2 or 3 times before the brick hit him on the head, witness told police. When police and medical personnel arrived, they found the victim unconscious and bleeding and airlifted him to the hospital. Yikes.
So there's two things going on here. First of all, been drinking too much. That's a bad thing. Second of all, should have taken physics.
Should have taken physics. No common understanding of physics whatsoever. Okay, don't be like him, and I hope he wasn't related to any of you guys.
That's right.
Okay, so should we have them do this one on their own?
They should do this one on their own.
Do this one on your own. A 0.5 kilogram water balloon is thrown straight up with a velocity of 10 meters per second. How high will it go? And they need to do the pyramid for this.
Yep.
We are relating, we want to know about UG here, the height here, and then we were given velocity, has to do with kinetic energy. Make it happen, people. And last but not least, do this one on your own. Your homework is chapter 11, page 270, number 57 and 59.
They can do this.
You can do it.